for this last section on Chapter 9. Section 7, we're now using our concept of definite integrals to link with the idea of linear motion. Major idea that you got to keep in mind for this is the connection between displacement, which we also call distance, to velocity to acceleration. Keep in mind that if you have a position function or a displacement function or a distance function, same thing, the derivative of that is velocity, and the derivative of velocity is acceleration. So remember how those moved kind of down the ladder that way. If you have any of those and you want to go back up the ladder, it's with doing an integral. Since velocity is the derivative of displacement, that means if I have the velocity and I'm trying to come up with the distance, then I need to integrate to go back up the ladder here to get to the displacement function. And that's really the main idea that you're seeing in this video. They're going to try to link it with some kind of real-life concept applications on this, but the main idea that you want to keep in mind is this one right here. And so if we were to talk about the distance traveled between two times, so the s of t is your position function or your displacement function. So if I want the distance traveled, then I'm going to take the ending time position minus the initial time position and come up with the total distance traveled. Well, if I don't have the position function to do that with, and I'm given the velocity function, well, then I need to integrate my velocity function in order to get the use of the displacement function. And so that's what you're seeing in this scenario right here. And so this is what we're doing when they ask us to find the total distance traveled, but they give us velocity to work with. And so we're integrating that velocity function in order to get the total distance traveled. As always, keep in mind, whenever you're dealing with the area under the curve, which is what an integral is, any part of that curve that would be below the x-axis puts out a negative result. And so the way we dealt with that in the past was to put a negative right here. Anytime it was below the x-axis, we put a negative in front of the integral so that we could change our negative answer into a positive. Well, the other way to do that would just be to put it in absolute value brackets so that it's going to become positive no matter where it is. Whether it's above or below the x-axis, this is going to make it positive. So look at a couple examples with me here. So you can see right here they're giving me a velocity function, and we're going to evaluate that. The first initial time was at 2, so this might be 2 seconds or 2 minutes or 2 hours. They didn't really state it in this case, but it's a value of 2 and then to a value of 5. And so if you're to think of this of the course of like hours, right, this would have been at the 2-hour mark, this would be at the 5-hour mark. And so if we want to get the total distance traveled, then we simply want the difference between the two times. And since we have a velocity function, we would need to integrate that in order to work with the distance function. And so we have our velocity function here. We have our initial time and our ending time. So we're going to evaluate this from 2 to 5. So just using the steps that we've done already this chapter, if you integrate that function, you get this look right here. We can now evaluate the integral from 2 to 5. And so if we plug in the 5, you get this look here, plug in the 2, and you get this look here. And after subtracting, we get the total distance traveled of 78. For those of you IB test taker people, keep in mind that if you are ever given units, you always want to include units in your answer. This goes for everything that could involve units. It involves areas, things with geometry, all those things. You always want to include units if units are given. IB marks for that. So again, on number 2, this is the same idea here for 2 and 3, just a couple different looks with the function. So on this one, 3 square root t plus 2. So here's the velocity function, and we want the total distance traveled from an initial point of 0 all the way up to 4. And so if we take our function right here, so again, just putting this in friendly terms, 3t to the 1/2 power plus 2. So we're going to integrate that guy first. So if you, as always, if you add 1 to your exponent and then divide by the exponent, so we added the 1 to get 3/2, we would then divide by 3/2, or you could say multiply by 2/3, and that's going to give you this look here. And again, for the second term, if you integrate the 2, it becomes 2t to the first over 1. And now we can evaluate that from 0 to 4, just like you're seeing it here to get the total distance traveled. As always, make sure that you show your work, especially on a test. Really important that this is seen. Oftentimes, this comes out wrong. So it's the work that will save you some points. So make sure that you always show good, clear work the way you're seeing on these. One more look on this. A reminder with an e function, those are nice and easy. The integral of e to the t power is just e to the t power. So when we go to integrate that guy, those e's are always easy. Here was the initial look. You can see that we're going to go from 0 to 10 for the total distance traveled. So give that one a try on your own. Not too much different about that one. Alright, this is the exact same idea, but in terms of a graph. And so in this problem, we have a velocity graph. And so the graph that you're seeing right here is represented by velocity. And they're still asking me the same question. They want to know the total distance traveled, and so that's what we're working with for this one. So in order to get the total distance traveled here, I need to find the area under the curve for each interval within this graph. And so I need to find the area of that triangle, the area of that triangle, and the area of that triangle, and add them together. And that's what part A is asking, is to just find the change in displacement for each of the 3 areas or the 3 intervals, and then add them together. Keep in mind, we can't just do it all in one shot from 0 to 16, because some of these are positive, some of these are negative, so we have to break it up and do it within the intervals, turn them all into positives so that we can get a total distance traveled on this. So one thing that IB likes to do is to throw in some questions like this that are just a slight change in the wording, just to make sure that you understand the concept and you can apply what you know to some slight changes within the wordings of the problem. So in this first part, when it says A, change in displacement, anytime you do a rate of change, rates of change can be negative. Distance is always positive. And so in a case like this, you can actually get some negative values, but when you do distance, it would always be positive. And so you got to understand the difference within the wording that you see right here. So if we just do the rate of change for each interval, and that's what you're seeing down here, well, how do I do that with my integral process if I do not have a function to work with? So one route that students will take on this is they try to create their own function. And so they say, well, this is just a line. Let's come up with a y equals mx plus b equation of that line, and they try to create functions so that they can do the integral process. But what you're supposed to see on problems like this is there's an easier way. When you deal with the integral process, because that is just the area under the curve, well, in this case, the area under this function is just a triangle. And so if I find the area of that triangle by doing 1/2 base times height, the area under that curve is the exact same thing for the area of the triangle, just like you would do with the integral process. And so for this problem, that would be the easiest way to go. So this is the area under the first triangle, which is 24. For this one, so and that was from 0 to 6. For the next one, from 6 to 10, we're just doing the area of that triangle. So again, we're doing the 1/2 base times height. Notice on this one, we do get a negative rate of change. Because it's below the x-axis, we do get a negative rate of change. And you can have a negative rate of change. You just can't have a negative distance. And so when we go to find the total distance traveled, we will turn this into a positive. But for now, to answer this question, we would leave it as a negative because it's below the x-axis. It doesn't represent distance yet. We're using this as rate of change. And then one last one, if you get the area of the third triangle, you see it's 6, and we'll keep that one positive because it's above the x-axis. But now to answer part B, when we say the total distance traveled, well, now for distance, we have to see them as all positives, and we get that 36. Just like when we did these with integrals in the past, when we did a total area under the curve, we have to do this concept right here and turn this into a positive in order to get the total area under the curve. So an area, if you're asked for area, that would be always positive, and distance is always positive, but again, the difference on this question was rate of change, and rate of change can be negative. All right, last one, and again, you can give this one a try ahead on your own if you'd like. So for number 2, so here we are again, we're given a velocity function for a total of 21 seconds. So you can see this goes from 0 to 21. And they want us to find the total distance traveled from 2 to 15. And so we're going to go from right here all the way over to 15. So there's a couple approaches you can take to this, but the main idea that you're supposed to get out of this is simply that distance is the integral of velocity. Therefore, it's the area under the curve. So if I'm just going to find an area, in a case like this, these are basic geometric shapes, and so I can just use basic geometry formulas to get the area that I'm looking for. From 0 to 15, which is what's kind of highlighted by this vertical bar and this vertical bar. So a couple ways you could do that. The way that you see it here is it's broken up into two easily found shapes. We're going to break this up into a rectangle and a trapezoid. And so if I just can find the area of both of those and add them up, then I'll get my total area under the curve from 2 to 15. So pretty much on this one you can just count. So just to count my length and my width of the rectangle, I can get that area right there. Area of a trapezoid is 1/2 the height times base 1 plus base 2. Remember that your bases in a trapezoid are always the parallel lines. So I would have to see this as a base and this as a base because they are parallel to each other, which means the height, the height is whatever connects your two bases together. So this line right here is going to be my height. And so if I just get those numbers, I can plug it into the formula the way that you're seeing here. And so this is the rectangle, base times height. This is my trapezoid. So that's base 1, base 2, and my height. And so I'm just going to add up the area of those two shapes to get the total area under the curve from 2 to 15. Certain times, a lot of the times on an IB question, they allow for both. For example, they will give you functions for the graphs, and so you'll get some functions for the graph, and so that you could either do it with a geometry process like this, or you can do it with an integral process with the functions. And so they like to give you options on that so that people, depending on how you see the work being done, you can take either route. But it's good to know both, because obviously in a case like this, we're not given functions to work with. You would actually have to create them in order to do this, and you don't want to have to do that. So it's easier if we just recognize that we can just deal with the geometry method of solving certain cases.